Hello, we propose 3D-GSW, 3D Gaussian Splatting for robust watermarking. In this research, we address the challenges of embedding digital watermarks into 3D Gaussian splatting models, enhancing robustness and real-time rendering. We proceed with our work in 3D Gaussian splatting. 3D Gaussian splatting represents 3D scene or object using 3D Gaussian primitives. This explicit representation enables real-time rendering and high rendering quality. Since rendering quality, training speed, and real-time rendering performance are ahead of previous radiance field model, 3D Gaussian splatting has become mainstream in radiance field research. 3D Gaussian splatting can be applied to various 3D fields, however, the importance of ownership protection is emerging. When we use traditional digital watermarking on rendered images, this cannot guarantee ownership protection if the model is stolen. Therefore, our goal is to integrate watermark process with rendering process. We fine-tune the pre-trained 3D-GS to ensure the rendered images from all viewpoints contain a binary message. Previous radiance field steganography method, steganerf, can be applicable to 3D Gaussian splatting. Steganerf is the first steganography method. Fine-tune the radiance field model to integrate watermark process with rendering process, and they propose adaptive gradient mask to enhance rendering quality. There are some limitations. Decoding the watermark requires the original image, which makes it hard to ensure robustness since the type of distortion applied to the image needs to be identified. The adaptive gradient mask cannot be used in 3D-GS because of a division by zero issue. Additionally, double rendering is required, which is inefficient. Here's another method for radiance fields watermarking. Watermark fine-tunes the model to combine the watermarking process with rendering. To make it more robust, they use discrete wavelet transform. Furthermore, they introduces a patchwise loss to enhance rendering quality. However, Watermark does not guarantee a large capacity watermark and does not account for model distortion. Additionally, the fine-tuning process is inefficient as it requires rendering twice. Previous methods are unsuitable for 3D Gaussian splatting due to it have numerous 3D Gaussians for high-fidelity rendering, leading to high memory and storage costs. Embedding large watermarks is computationally expensive and time-consuming, while many 3D Gaussians have minimal impact on the rendered image, interrupting robust watermark embedding. To address these issues, we propose 3D-GSW. These are our contributions. We propose frequency-guided densification to effectively remove 3D Gaussians without compromising the rendering quality, to embed a robust message in the rendered image while enhancing the real-time rendering. We propose a gradient mask mechanism that minimizes gradients to preserve similarity to the pre-trained 3D-GS and maintain high rendering quality. The proposed method achieves superior performance and demonstrates robustness against various types of attacks, including both image and model distortions. Now, we will introduce our method, 3D-GSW. Our goal is to fine-tune 3D Gaussian splatting model to render watermarked images. If model is fine-tuned with 3D-GSW, novel view images are embedded with a watermark without additional process. If someone steals a model, they can distort either the rendered image or the model itself, attempting to remove the watermark. However, if the model has been fine-tuned by our method, watermarks can be detected even for such distortions. Here is overview of our method. Before fine-tuning, frequency-guided densification removes 3D Gaussians based on their contribution to the rendering quality and splits them in high-frequency areas. We also construct a gradient mask based on the parameters of an FGD-processed model. Unlike other methods, we render only once per iteration during the fine-tuning. Then, we apply DWT to the rendered image, using the low frequency as input to a pre-trained decoder. For reconstruction loss, we measure the difference between the original image and the watermarked image. For LPIPS loss, we evaluate the perceptual similarity between the feature maps of the original image and the watermarked image. LPIPS loss is typically computed by extracting feature maps from a pre-trained neural network. For wavelet subband loss, we transform the images to several wavelet subbands. Using DWT, we only employ high-frequency subbands to improve the rendering quality in high-frequency areas. We employ mean absolute error between the original high-frequency subbands and watermarked high-frequency subbands. For message loss, we employ a sigmoid function to confine the decoded message within 0 to 1. The message loss is a binary cross-entropy between the fixed message and decoded message through sigmoid function. 3D-GS is optimized through the total loss, which consists of reconstruction loss, LPIPS loss, wavelet subband loss and message loss. The gradient is calculated with our gradient mask and then transmitted to 3D-GS. This is more detail about frequency-guided densification. FGD consists of two phases. In phase 1, we remove 3D Gaussians with minimal impact on the rendered image before fine-tuning process. The contribution of each 3D Gaussian to the rendering quality is calculated by the auxiliary loss function about pixel color error. In phase 2, 3D-GS, that remove 3D Gaussians, renders images, and these images are divided into patches. To find strong intensity of high frequency, we transform the spatial domain patches to frequency domain patches, using DFT. To measure intensity of high frequency, we design a mask to emphasize high frequency signals. Through the mask, we can get the intensity of high frequency, and select top K percentage patches. Finally, we split 3D Gaussians in that patches. After FGD process, models still render high-quality images. We propose a gradient mask to maintain this quality, using an exponential function. We create the mask Z for each parameter color, opacity, rotation, scale. During optimization, the gradients is masked by Z to reduce their size. Since small gradients are transmitted to model, the parameters of model become similar to the original ones. During phase 2 of FGD, we modify 3D Gaussians in the high-frequency areas. To enhance the rendering quality of these high-frequency areas, we introduce a wavelet subband loss. To analyze local details, we use the discrete wavelet transform and focus on the high-frequency subbands, LH, HL, HH. We calculate the mean absolute error between the high-frequency subbands of the original image and the rendered image to refine the quality further. Now we show our quantitative results. The quantitative results for 3D-GSW, comparing bit accuracy and rendering quality across various methods and bit lengths. 3D-GSW consistently outperforms existing watermarking methods, such as Steganerf and Waterf, across 32, 48, and 64 bits, even at higher capacities like 64 bits. 3D-GSW maintains robust bit accuracy and superior image quality, demonstrating the effectiveness of the proposed method. Additionally, the result of 3D-GSW without FGD confirms that FGD further improves both bit accuracy and rendering quality. The top table evaluates robustness against image distortions. 3D-GSW consistently achieves the highest bit accuracy under all types of distortions. The bottom table shows robustness under model distortions. Even when Gaussian noise is added or 3D Gaussians are removed or cloned, 3D-GSW maintains strong performance. This confirms its resilience across both image-level and model-level attacks. Bit accuracy for Waterf, Steganerf, 3D-GSW without FGD, and our method for image distortions and distortion strengths. Our method outperforms other methods. Bit accuracy for Waterf, Steganerf, 3D-GSW without frequency-guided densification, and our method for model distortions and distortion strengths. Our method outperforms other methods. This table highlights the efficiency of 3D-GSW. It significantly reduces fine-tuning time to just 21 minutes, while also increasing rendering speed to over 72 FPS. Additionally, storage is reduced, demonstrating the effectiveness of our method. Now, we present ablation study. We remove each component in our method and compare the rendering quality with the bit accuracy, these results show the importance of each component in achieving a good balance between the rendering quality and bit accuracy. This shows why we only use high-frequency subbands. Using only high-frequency subbands improve rendering quality more effectively. This is the impact of 3D Gaussians removal. From 10 power of -10 to 10 power of -8, bit accuracy improves while rendering quality is maintained. For objects without a background, our method effectively adjusts 3D Gaussian parameters to prevent rendering beyond the object's boundary, preserving the original quality. The exponential function makes it similar to the original parameters even after fine-tuning. Furthermore, the gradient mask with exponential function make a good balance between rendering quality and bit accuracy. Now, we show our qualitative results. We achieve high rendering quality compared to other methods. We achieve high rendering quality compared to other methods. We achieve high rendering quality on the Blender datasets. We achieve high rendering quality on the Blender datasets. We achieve high rendering quality on the LLFF datasets. We achieve high rendering quality on the LLFF datasets. We achieve high rendering quality on the MIP-NERF 360 datasets. We achieve high rendering quality on the MIP-NERF 360 datasets. More experiment results and detail in our main paper and supplementary material. Thank you.